Hi everybody, this video is going to be about finding the difference quotient and using it in the TI nSpire CAS calculator. So let's get started. I'm going to make a new document, add a calculator to it, and we need a function to work with. There are lots of ways to define functions in the calculator. One way to do it, click Menu, Actions, and Define. If you're on a keyboard like I am, it's actually faster to just type the word define, but in the handheld calculator, Menu, Actions, Define is probably a bit faster. I'm going to call this function f1. If I name it f1, then later on, if I wanted to graph the function, I can. So let's just define a function like this. I define the function in this way because there's a physical interpretation here. We're talking about an object that's thrown straight up in the air with an initial velocity of 160 feet per second and an initial height of 10. So there's something physical we can think about with a function like this. Negative 16 is due to the force due to gravity. So our difference quotient would be f1 of x plus h minus f1 of x over h. Now I could literally type that in the nSpire CAS calculator, and it's perfectly capable of dealing with that symbolically. However, we can do something a little bit nicer since we have an nSpire CAS calculator. I'm going to define a new function. I'm going to call it diff for difference quotient. So let's think for a second. The difference quotient, f of x plus h. There's two letters there, x and h. Now, our interpretation of those is really important. X is a moment in time in this example because we're talking about an object going up and then coming back down. H tells us an interval of time. What I can do in the calculator, though, is define a function in two variables. So I'll be able to substitute a value for x and a value for h. And now I'll type just my formula for difference quotient, which is f1 of x plus h minus f1 of x over h. There we go. So if I just want the difference quotient in pure abstract symbolism, I can type diff of x comma h. So this is just going to substitute x and h into this formula, which is strictly the difference quotient. And there's what it is. Now, if you did this by hand, the negative 16 would you'd probably automatically have it distributed into the parenthesis. It doesn't really matter. The nSpire will often do a little factoring. So the difference quotient for our function is negative 16 times 2x plus h minus 10. The little yellow caution symbol, the nSpire uses that if you have something defined and there's a variable in the denominator, the calculator is just telling you, hey, we did some simplifications, but remember canceling by zero is not really allowed, so just be careful. That's all the yellow triangle means. So this is our difference quotient. Yay, we're done. But I mean, the difference quotient is actually really powerful. We can do things with it. So for example, if I type this, my interpretation is I'm finding the average rate of change of this object between 3 seconds and 3.5 seconds. That's the way we interpret this h. So we're starting at 3 seconds and we're going for half a second. So if I press enter, the average rate of change of this object, or the average speed of this object between 3 and 3.5 seconds is 56 feet per second. That's great, but we can keep going. If I shorten my time interval, I see that the average speed is 62.4 feet per second. So that's from 3 to 3.1 seconds. That's a pretty small time interval, but I can keep going. Over this interval of 1/100th of a second, so from 3 to 3.01 seconds, the average speed of the object was 63.84 feet per second. Now, if you've seen this before, you're starting to get suspicious and you see where this is going. So over this time interval of 1/1000th of a second, from 3 to 3.001 seconds, the average speed of the object is 63.9, very close to 64 feet per second. Now at this point, you can probably conclude that not an average speed, but the instantaneous speed, the actual speed of the object at 3 seconds is 64 feet per second. You can keep going if you don't believe that, but do this as much as you want, make this interval as small as you want. The average speed is going to get closer and closer and closer to 64 feet per second. Now to really draw that conclusion, you're going to need to take some calculus. But for our purposes, we'll just use some inductive reasoning here and conclude that the average speed at the instantaneous speed at 3 seconds is 64 feet per second. So that's what we need to be able to do in the calculator, and of course be able to do this by hand as well. So define a function, use your calculator wisely. We paid a lot of money for these calculators, we might as well learn how to use them, and then interpret the difference quotient. I just want to mention one more thing. Since I called this function f1, I can graph it without doing any extra work. If I simply add a graphing window to this document, notice it starts at f2, and the reason is I already have f1 stored. So since I defined it in the calculator, it's already here in my graphing page. So if I just press enter to turn on the graph, I can see the graph. Now, I can't see very much because we're talking about an object that's going really fast. I like to change the window settings manually. I don't like the zoom features, although they work. Our x-axis is time here. Even though the object is going up with a pretty large initial velocity, probably going out to 15 seconds will do the trick. And then it's probably going to go pretty high in the air. I don't know, maybe 500 feet will work. You can always change the numbers later if you didn't make very good guesses. So here we go. Here's our object. It goes up, it comes back down, and what we just proved is at 3 seconds, so that would be around here, the average speed, the slope of this graph is about 64 feet per second. Once you take calculus, you can really dive deep into this, but that's not our purposes for now. So anyway, just wanted to make a video about using the calculator. I'll make a few more. See you next time.